Okay, so we went to regression. Now we're going to go into logistic regression. Logistic regression is another kind of regression. And here it is, our PowerPoint. When do we use logistic regression? When our y variable is an attribute. Okay, so remember this table, very, very important table. We have to know that. Okay. And there's another one with a little bit more information. Maybe that's the best one to kind of print it and plastify, put it in your wallet, and look at it all the time. Or maybe the screen, the back screen of your cell phone. This table, everything you need to know. Take out that stupid picture that you have there. So, when regression models, I have x variables that could be continuous or attribute, but my y variable has to be continuous for regression. For logistics regression, the x variables again could be continuous or attributes, but the y variable is an attribute. Okay, so output is either yes or no, or more than, it could be more categories. But basically, what you're going to see, which is the most used one, is the kind of a 0-1 situation, is either yes or either no. And we're testing how, for example, you're looking at a decision of buying a product or not, right? What is the impact in buying a product? So you can only have two outputs. You either buy the product or you don't buy the product. And maybe you're going to measure, how long it look to the product, how many colors the product have, what is the font size of the letters, how many pictures it has, does it have an image of something, yes or no? So there are a bunch of different variables that can impact. What is let's say that you were looking at a decision to buy a product in a grocery store, right? What is the width of the products that you can see in the shelf, right? When you're deciding to buy a product, what are the colors? A bunch of things can impact in your decision. What is the price to buy the product, yes or no? But your decision, which is the y variable, is only yes or no. Okay. So it is that basically what you're doing is calculating, using those x variables to calculate the probability of doing yes versus the probability of doing no, right? It's going to be 100% for the sum of both, right? But depending on, let's say the price and the color and how much space you have, and these things might impact the way that you make your purchasing decision, for example. We're going to take a look at the example. It's not a purchasing decision. It is actually come from a Capstone Consultant project that were done in Colonial Life. And here, what we're looking at as an insurance company is the probability of someone having an accident or not, right? So that will be the y variable, the likelihood of having an accident. So either you had an accident or you didn't have an accident, right? So 0 or 1. In the next 5 years. They looked at 72 variables and over 6 million of rows, right? So individual observations from year 2006 to 7, and are using a p-value of 15. 50%. So this is the logistics table, how the data look like. So for every observation, you have your y variable, which is accident. 1, you had an accident. 0, you didn't have an accident. Then we're going to look, we're not going to do 72 variables just to make your life more miserable. We're going to do only 3 to make your life more easy. Okay, so remember that when you're doing the course evaluations. We're going to look at age, vision, and driver's education. So vision means if you wear glasses or not, like I do. And if you had driver's education test in the last certain amount of time, certificate course. Okay. This is how you run it. It's stats, regression, binary, logistics regression. And we're going to go over and take a look at the results. Okay. So what it's doing is basically doing a regression model like the other one. So some of the things are the same. And then testing if there is a value for the constant there, the beta there, that is higher than 1, right? So if there is an impact on that from that variable into the likelihood, okay? So as you can see here, we have constant, age, vision, drivers, education. We have the coefficient, and we have the p-values here, okay? So since we're doing a critical of p 15%, you divided that by 4, you get a 0.375, okay? So from this critical value of 0.375 that we're using, which variables are significant? Well, vision and driver's education, right? So age is not, right? It doesn't impact. And you might think of why, right? So when you are young, you have more or less likelihood of having an accident. Probably more, right? When you're really young, you just got your driver's license, you have less experience, you have more accidents, right? When the first 5 years after I started, I took my driver's license, I was involved in a lot more stuff than the last 5 years, which is basically nothing happened in the last 5 years. And okay, when you get more experience, you have less accidents, right? But what happened when you're really old? Well, then your vision started to deteriorate a little bit, and you got a little bit slower in your instincts and all that, and you probably have more accidents, right? So that could also be something that is like, remember what it was? Polynomial order inverted, or so, and that will not capture here because it's a logistics regression. It's assuming a linear relationship there. Right? So it's assuming that it will increase X, it will increase Y or decrease Y, right? So that's maybe why we didn't capture age in this one. Anyway, this is our model now, right? Y equals to 1.7 something, 719, where is it? Here, 1.709, which is the coefficient of vision, times, if you have a vision, yes or no, minus 1.49, blah, 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 if you have a driver's education or not, and it will give you a value, right? And that value is the likelihood of having an accident. And here I create a table just to explain the scenarios, right? So we basically have two attributes variables that impact in an attribute variable as well, right? And that's the Y variable at the end. And then you have, you basically have those two attributes are yes or no, right? So we have 4 different scenarios that can happen. Can happen, have a vision problem and a driver's did driver's education. So you change the values to 1 for those in the equation. Remember the equation here? You just change this to 1 and this to 1, right? That's what I did. Is 0.21. 0.21 is less than 50%. So that person probably is not going to have an accident. It's unlikely, sorry, to have an accident. If you have use glasses and you haven't done the test, then the value will be 1.7, which is higher than 50%, 0.5. So yes, you're very likelihood of having an accident. If it's 0 to 1, it's minus 1.49, so very unlikely. So that goes to 0. If it's 0, 0, it's also unlikely because it's less than 0.5. So 50% is the middle, and whatever is below that, we're considered not having an accident. Whatever is higher than that, we're considered having an accident. So this is kind of the result of the logistic regression model. And now we're going to ANOVA, which is very, 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 very fun.